Hi, welcome to this course on vibration mitigation measures. In this course, I will talk about the need for controlling vibration levels, the sources of the vibrations, the devices that can be installed to reduce vibration levels, and the types of analysis required to perform the tuning of a vibration mitigation device for a particular problem. The course is structured as outlined on this slide. I will start with a brief overview of the consequences of excessive vibration levels and thus the need to keep them under control. Then I will present some of the frequently used damping devices. After that, I will touch on the analysis procedures and the optimization of the damping characteristics. The previously mentioned aspects will be illustrated by an example, the study of how a tuned mass damper changes the vertical vibration levels of a short railway bridge. Sometimes vibrations are beneficial for the health of people. However, there are also cases where vibrations generate discomfort or even damage to human beings and also to structural components. For example, the existence of guidelines on hand and arm vibrations clearly shows that there is a need to limit the exposure of people to this type of vibrations in order to prevent permanent damage from occurring. The same is true for building or mechanical vibrations where corresponding guidelines exist. The source of vibrations are quite diverse. For example, rotating machines are found anywhere from residential buildings to industrial plants. All sorts of engines generate vibrations and you can find them in every household. The dominant frequencies of vibrations may be quite different. From a 5 megawatt wind turbine may have a rotor speed of 12 rpm or 0.2 Hz, whereas a turbocharger of an internal combustion engine may rotate at 240,000 rpm or 4,000 Hz. But not only rotating machines can generate vibrations, moving loads also can. So, when we walk, with every step we take, a transient contact force is transmitted to the ground. If the walking speed is kept constant, these contact forces result in a periodic loading. Back in the 19th century, several bridge collapses are at least partly attributed to this type of periodic loading when soldiers crossed a bridge at constant marching speed. But also wind loads can result in significant vibrations of bridges or structures with low natural frequencies. The Tacoma Narrows cable-stayed bridge, shown on the slide, is perhaps the most famous bridge collapse attributed to wind loads. Obviously, earthquakes can also generate vibrations that sometimes result in huge damages. Sometimes human-induced loading results in significant vibration levels. A famous example is the Millennium Bridge in London, which had to be closed only a few days after the opening due to excessive vibration levels. To reduce the vibration level of some sort of damping device is installed. There are several devices available that differ in various aspects. For example, we all know what a fluid viscous damper looks like because nowadays you can even find them in a mountain bike suspensions. Hysteretic dampers are built of metal sheets that sandwich rubber-type material to provide supplemental damping. Hysteretic viscous dampers combine the damping characteristics of viscous and hysteretic dampers in a single device. Tuned mass dampers are built of masses that are connected to the main structure by a spring and in some cases by a damper that acts in parallel with the spring. The mass and spring of the tuned mass damper are tuned to the frequency of the mode of the main structure that contributes significantly to the vibration level. The idea is to divert part of the vibrational energy around this frequency to the tuned mass damper in order to reduce the energy that is available for the main structure to vibrate. Tuned liquid dampers are similar to tuned mass dampers in that part of the vibrational energy is used to put a fluid mass into motion. On the slide, a mode shape is presented that was obtained by the modal acoustics analysis system. The deformed shape is presented as exaggerated scale. Obviously, the water tank has to be tall enough to prevent water from leaving it. The existence of nonlinear behavior reduces the number of analysis procedures that are applicable. The nonlinear behavior can come from the main structure or from the damping device. Nonlinear time history analyses are very time-consuming, so if there is only a slightly nonlinear behavior, one can use a linearized model to optimize the parameter of the damping device, and after that confirm the results by performing a nonlinear analysis. In the ANSYS product portfolio, there are several analysis systems to perform transient dynamic analysis. To choose the most efficient analysis method for a particular problem, the type of nonlinearity and the duration of the simulation should be taken into account. If a linear model is appropriate, a variety of methods can be used to speed up the analysis process. For example, model decomposition can be used to reduce the model size, so instead of dealing with thousands of degrees of freedom, a much smaller number of model coordinates is used to solve the problem. Solution method involving a convolution integral or the Fourier transform can also be used. This opens the door to use a highly efficient method like the fast Fourier transform. The vibrations generated by rotating machines in industrial plants can often be studied using an harmonic analysis, as these machines operate constantly. There are only very few startups or shutdown events, so the main focus is on the vibrations generated during normal operation. Just as a reminder, harmonic analysis is limited to linear systems. There are several types of harmonic analysis the user can choose from. The most versatile option is the full harmonic analysis, where the coupled system of equations is solved. To speed up the analysis process, model decomposition can be used to reduce the number of unknowns and the model size. If the damping is proportional or a model damping is used, real-valued modes are used to decouple the system of equations, whereas in the case of non-proportional damping, complex-valued modes are required to achieve this goal. Model decomposition has also the advantage of making it easier to define frequency clusters, as the model frequencies are known before starting the harmonic analysis. The progress of digital media reduces steadily the amount of paper in the office. In addition, the number of printers and copiers is reduced. As a result, the dynamic characteristics like mass and damping are changing. If a damping device is installed to limit the floor vibrations, these changes may render it less effective. In this case, it would be very useful if the properties of the damping device could be adjusted. Another case where the adjustment of the properties of the damping device is recommendable is when there is no reliable data of the dynamic characteristics of the main structure. This is usually the case for new buildings. Quite often, the excitation characteristics change during the life of a building or structure. For example, if a damping device is very efficient only in a narrow frequency window, and the excitation frequency moves outside of this window, what can be done to recover at least part of the efficiency? All these scenarios require dynamic analysis to study the possible outcomes. Although these examples are from civil engineering, similar situations exist in other engineering disciplines. The example deals with a vibration problem that was observed in France when the first generation of high-speed trains entered in service in the 90s. They observed that the maintenance interval of short railway bridges were very short in comparison with the rest of the line. An investigation revealed that large vertical bridge deck accelerations were caused a rapid degradation of the track geometry. The track conditions were reproduced in laboratory, and they found that at accelerations of about 0.7 g, some stones of the ballast bed start to move and leave their position. To prevent this from occurring, the authorities established a limit value of 0.35 g, so they applied a factor of safety of 2. Today, a dynamic analysis is required for new bridges to check that the limit value is not exceeded. To this end, FE models are used. The guidelines consider different types of load models. The simplest one corresponds to moving point loads where each point load represents one train axle. For straight single-track bridges, a beam element model may be appropriate. In case of multi-track bridges and non-homogeneous geometries, shell element models may be more appropriate. The design codes prescribe to cover certain speed ranges, so there are dozens of transient dynamic analysis necessary for a single train type and each direction of travel. As several train types are usually analyzed, the number of runs corresponding to a single bridge design may quickly exceed 100. Therefore, there is always the incentive to reduce the number of degrees of freedom by choosing the least sophisticated FE model. Example: tuned mass damper. In general, the moving point loads may or may not act at a mesh node. If the load happens to act on an element, equivalent nodal forces have to be calculated. Just as a reminder, the equivalent nodal forces should be calculated using the shape functions of the used finite elements. In the case of beam elements, there are forces and bending moments. The use of a linear interpolation function, i.e. the hat function as indicated on the slide, also being only an approximation of the equivalent nodal forces, yields good results when used in combination with small elements. The smaller the beam elements are, the smaller are the bending moments the load produces. So neglecting them can be justified when small elements are used. To define moving loads, APDL tables can be used. The load is defined as function of time and a spatial coordinate, and at each time step the load is automatically determined by interpolation. When using a convolution integral to calculate the structural response of a linear time invariant system, the dynamic reciprocity theorem is applicable. So if the goal is to calculate the response of a single degree of freedom, all required impulse response functions can be obtained in a single run, applying the corresponding force at the degree of freedom of interest. In the case of simply supported railway bridges, the maximum vertical bridge deck acceleration is often produced at mid-span. So, as indicated on the slide, the application of a vertical point load at mid-span yields all the required impulse response functions to calculate the response at mid-span. As the impulse response functions are a system property, they are independent from a particular load case. This bears the advantage of having to calculate them only once. For this example, the German ICE-2 high-speed train is used. On the slide, the axle load distribution is displayed as function of the axle position. The distance between the first axle and the last axle is 350.52 meters. At the extremes, the motive power units are located, which is clearly visible as the corresponding axle loads are considerably higher than the axle load of the passenger cars. There are several distances that are constant, like for example the distance between two axles of the same bogie, or the distance between bogies. The combination of these distances with a constant traveling speed results in a periodic loading pattern which excites certain frequencies. If one of these frequencies is close to a modal frequency of the bridge, the dynamic amplification may be quite significant. The maximum response doesn't have to occur at maximum speed. Quite often, the peak response occurs at speeds much lower than the maximum speed. As the rolling stock manufacturers can use different bogie configurations that result in different characteristic distances, different trains may excite different frequencies at the same traveling speed. Depending on the type of railway track, ballasted or slab track, different limit values apply. The more stringent limit of 3.5 meters per second square correspond to ballasted track. For this example of a straight single-track bridge, a beam model has been used. At a speed of 230 km per hour or 63.9 meters per second, it takes 5.7 seconds for the train to cross the bridge. Two time histories are shown on the slide. The upper one is the displacement, and the lower one is the acceleration time history, both at mid-span. In case of single-span bridges, the maximum response is produced quite often at mid-span. In the displacement time history, the effect of the higher axle loads of the motive power units are apparent. At the beginning and at about 5.5 seconds, a total of 4 through are visible, one for each bogie, one of the two motive power units. After the train exits the bridge, the both charts look much like the free vibration response of a single degree of freedom system. In some cases, the maximum acceleration is registered at the beginning of the free vibration phase, just after the last axle has exited the bridge. The operational maximum speed of the ICE2 is 280 km per hour. During homologation runs, the top speed may be higher. For this example, the speed range between 150 and 350 km per hour has been covered in increments of 5 km per hour. The graph on the slide shows the maximum vertical acceleration at mid-span versus speed. Several peaks are apparent, the first one around 160 km per hour and the second one around 230 km per hour. This last one is particularly important because the acceleration exceeds the limit value of 3.5 meters per second squared for ballasted tracks, and the speed is well below the operational maximum speed. At 335 km per hour, even the higher limit value of 5 meters per second squared is exceeded. To reduce the maximum acceleration level, a TMD is installed at mid-span where the fundamental mode shape has its maximum value. The TMD is not fine-tuned, but only set up to have the same natural frequency as the fundamental mode of the bridge. The idea is that, due to the installation of the TMD, the vibrational energy in this frequency range is shared between the bridge and the TMD, thereby reducing the energy available for the bridge to vibrate. Obviously, the size of the TMD mass should be as small as possible, as it adds to the self-weight of the bridge. Also, the smaller the TMD device is, the easier its installation will be. The mass of the TMD plays a crucial role. A larger mass usually results in lower structural response. The TMD mass itself may get too much higher acceleration levels than the bridge, but this is not a problem. It is designed to safely operate at these levels. In a first attempt, one TMD has been added to the FE model. To study the influence of the TMD mass, 3 different sizes have been analyzed: 5 tons, 7.5 tons and 10 tons. The damper of the TMD has been adjusted to a damping ratio of 8% of critical, considering the TMD as single degree of freedom system. The smallest TMD provides already considerable reduction of the maximum acceleration levels, particularly the first 2 peaks at 160 km per hour and around 230 km per hour are greatly reduced. In the graph, the results are shown as a yellow curve. However, at speed above 255 km per hour, the limit value of 3.5 meters per second squared is still exceeded. By increasing the TMD mass to 10 tons, the acceleration levels are even further reduced, and up to 320 km per hour, the limit value is not exceeded. In an attempt to reduce the TMD mass, the size of the first TMD is reduced to 7.5 tons, and a smaller TMD of 1 ton is added at mid-span. This one is tuned to the model frequency of the third bending node. The second bending mode has a model node at midspan and does not contribute at all to the vertical response at this point. As a result, the acceleration limit is not exceeded up to 310 km per hour. Additional adjustments would yield better results. Even the installation of the smallest TMD of 5 tons reduces the maximum vertical acceleration well below the limit value of 5 meters per second squared, corresponding to the slab track. In the case of a TMD, the vibrational energy is dissipated by the damper. However, part of the energy may also be converted into electrical energy, which can be used to power some of the electrical devices installed on the bridge. So energy harvesting is also an application where tuning is necessary, though in this case to maximum the power output. All the analyses are based on models, and in a perfect world these models represent the relevant features of the real-world physics. However, we all know that the model only yields approximation to real-world behavior. Calibration of the FE model by experimental data is very valuable and should be done whenever possible. If a linear model can be used, a broad spectrum of methods can be applied that can drastically reduce calculation times in comparison with step-by-step time integration methods. If the solving time of a single run is short, the optimization method offered by ANSYS can be applied very efficiently. ANSYS offers a huge toolbox of analysis systems. However, the quality of the results not only depends on the tools but also on the user. A good understanding of the fields of application and the limitation of these tools is crucial to make adequate use of them. The master program of the Polytechnical University of Madrid offers several courses in solid as well as fluid mechanics to improve the knowledge of the students in these areas.